Chemical grounding electrodes, often referred to as ground rods, represent a specialized approach to grounding electrical systems. The fundamental principle of any grounding system is to provide a low impedance path for fault current to return to the source, thereby facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of faults minimizes the risk of electrical shock hazards and equipment damage. Conventional grounding electrodes typically consist of copper or copper-clad steel rods driven into the earth. The effectiveness of these rods in providing a low impedance path depends largely on the soil resistivity in the surrounding area. High soil resistivity, often encountered in dry or rocky environments, can significantly impede the flow of current, making it difficult to achieve the desired grounding resistance. Chemical grounding electrodes are designed to address this challenge. These electrodes typically consist of a hollow tube filled with a specialized chemical compound. This compound is designed to leach into the surrounding soil, reducing its resistivity and thereby improving the effectiveness of the grounding electrode. The chemicals used in these electrodes are typically hygroscopic, meaning they attract and retain moisture from the atmosphere. This moisture helps to dissolve the chemical compound and facilitate its migration into the soil. By reducing the soil resistivity, chemical grounding electrodes can achieve lower grounding resistance compared to conventional ground rods, particularly in areas with poor soil conditions. The installation of chemical grounding electrodes typically involves driving the electrode into the ground in a similar manner to conventional ground rods. However, additional steps may be required to ensure proper chemical leaching and electrode performance. These steps may include watering the surrounding soil or adding additional chemical compound to the electrode. The use of chemical grounding electrodes is governed by the National Electrical Code, specifically Article 250. The NEC outlines the requirements for grounding and bonding electrical systems, including the acceptable types of grounding electrodes and the methods for their installation. Section 250.52 of the NEC specifies the types of grounding electrodes that are permitted, which include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and rod and pipe electrodes. While the NEC does not explicitly prohibit the use of chemical grounding electrodes, it does require that all grounding electrodes meet certain performance requirements. Specifically, Section 250.56 requires that the grounding electrode system have a resistance to earth of 25 ohms or less. If the resistance exceeds 25 ohms, the grounding electrode system must be supplemented by an additional electrode. The effectiveness of a grounding electrode can be significantly impacted by soil conditions such as moisture content, temperature, and the presence of minerals. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity indicates that the soil is a good conductor, while high soil resistivity indicates that the soil is a poor conductor. Soil resistivity is typically measured in ohm meters or ohm centimeters. Several factors can influence soil resistivity, including moisture content. The higher the moisture content, the lower the soil resistivity. Temperature. Soil resistivity decreases as temperature increases. Mineral content. The presence of certain minerals, such as salts, can lower soil resistivity. Soil type. Clay soils typically have lower resistivity than sandy soils. When selecting a grounding electrode, it is important to consider the soil conditions at the site. In areas with high soil resistivity, it may be necessary to use a chemical grounding electrode or other specialized grounding techniques to achieve the required grounding resistance. Ground resistance testing is an essential part of ensuring the effectiveness of a grounding system. Ground resistance testing involves measuring the resistance between the grounding electrode and the earth. This measurement provides an indication of how well the grounding system is able to dissipate fault current into the ground. Several methods are available for measuring ground resistance, including the fall-off potential method, the clamp-on method, and the three-point method. The fall-off potential method is the most accurate and widely used method for measuring ground resistance. This method involves injecting a test current into the earth and measuring the voltage drop between the grounding electrode and a remote reference electrode. The ground resistance is then calculated using Ohm's law. The clamp-on method is a convenient method for measuring ground resistance in situations where it is not possible to disconnect the grounding electrode. This method involves clamping a specialized meter around the grounding electrode and measuring the current flowing through the electrode. The ground resistance is then calculated based on the measured current and voltage. The three-point method is a simplified method for measuring ground resistance that can be used in situations where a high degree of accuracy is not required. This method involves driving two auxiliary electrodes into the ground and measuring the resistance between the grounding electrode and each of the auxiliary electrodes. The ground resistance is then calculated based on the measured resistances. Proper grounding is critical for ensuring the safety and reliability of electrical systems. A well-designed and properly installed grounding system can protect people from electrical shock hazards, prevent equipment damage, and minimize the risk of fire. Regular inspection and testing of grounding systems are essential to ensure that they are functioning properly. Some common grounding system problems include corroded or loose connections, damaged grounding conductors, and high ground resistance. Any of these problems can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. When inspecting a grounding system, it is important to check all connections for corrosion or looseness. Corroded connections can impede the flow of current and increase ground resistance. Loose connections can also create a high resistance path, which can prevent the grounding system from functioning properly. It is also important to inspect the grounding conductors for damage. Damaged grounding conductors can reduce the effectiveness of the grounding system and increase the risk of electrical hazards. If any problems are found with the grounding system, they should be repaired immediately by a qualified electrician. The cost of chemical grounding electrodes can vary depending on the size and type of electrode, as well as the manufacturer. Generally, chemical grounding electrodes are more expensive than conventional ground rods. The increased cost is due to the specialized chemical compound used in the electrodes and the more complex manufacturing process. However, the increased cost may be justified in situations where conventional ground rods are not able to achieve the required grounding resistance. Factors influencing the cost of chemical grounding electrodes include electrode size. Larger electrodes typically cost more than smaller electrodes. Chemical composition. The type of chemical compound used in the electrode can affect the cost. Manufacturer. Different manufacturers may charge different prices for similar electrodes. Installation costs. The cost of installing chemical grounding electrodes may be higher than the cost of installing conventional ground rods due to the additional steps required to ensure proper chemical leaching and electrode performance. When evaluating the cost of chemical grounding electrodes, it is important to consider the long-term benefits of improved grounding performance. A well-designed grounding system can protect equipment from damage, reduce the risk of electrical hazards, and improve the overall reliability of the electrical system. These benefits can outweigh the initial cost of the chemical grounding electrodes. In addition to chemical grounding electrodes, other specialized grounding techniques can be used to improve grounding performance in areas with high soil resistivity. These techniques include ground enhancement materials, ground grids, and counterpoise systems. Ground enhancement materials are used to improve the conductivity of the soil surrounding the grounding electrode. These materials typically consist of a mixture of minerals and chemicals that are designed to reduce soil resistivity. Ground grids are a network of interconnected grounding conductors that are buried in the earth. Ground grids provide a large surface area for dissipating fault current into the ground, which can help to reduce grounding resistance. Counterpoise systems consist of a network of grounding conductors that are installed above ground, typically parallel to overhead power lines. Counterpoise systems provide an alternative path for fault current to return to the source, which can help to reduce the voltage drop along the power lines. The selection of the appropriate grounding technique depends on the specific site conditions and the performance requirements of the electrical system. A qualified electrical engineer can help to evaluate the site conditions and select the most appropriate grounding technique. Regular maintenance and testing are essential for ensuring the long-term performance of grounding systems. Grounding systems should be inspected regularly for corrosion, damage, and loose connections. Ground resistance testing should be performed periodically to verify that the grounding system is still meeting the required performance standards. If any problems are found with the grounding system, they should be repaired immediately by a qualified electrician. In conclusion, chemical grounding electrodes represent a specialized approach to grounding electrical systems that can be particularly effective in areas with high soil resistivity. While they may be more expensive than conventional ground rods, the improved grounding performance can justify the increased cost. Proper installation, maintenance, and testing are essential for ensuring the long-term effectiveness of chemical grounding electrodes and other grounding systems. The National Electrical Code provides detailed requirements for grounding and bonding electrical systems, which should be followed to ensure the safety and reliability of electrical installations. When dealing with electrical systems, always consult with a qualified electrician to ensure that the work is performed safely and in accordance with all applicable codes and regulations. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. Grounding and bonding are critical for protecting people from electrical shock hazards, preventing equipment damage, and minimizing the risk of fire. By following the requirements of the National Electrical Code and best practices for grounding and bonding, it is possible to create safe and reliable electrical systems.